Okay. So I put up the statistics with the exams. Um, as a whole, actually, the class did pretty decent. We had a good number of students with 90% or above. I would say we had a very good number of students with 80% or above. Uh, I would say if you wanted to internally curve, if I curve, I curve at the very end. If you wanted to internally curve, I would say that the exam was probably about 12 points too hard. So if you mentally added 12% to whatever you got, that's probably where it would have curved to if this was like the final exam or something. It'll ultimately curve at the end. I'm not, I'll distribute overall grades, reasonably, but with that, there'll be several students who got significantly above 100 on the exam. That doesn't mean that if you didn't do that, that you're failing. I would say that if we take into consideration um, that little curve, if you got 45% or better on the exam, it's probably you're just waiting for it to finally click, or maybe you just need to work just a little bit harder. It means you largely knew what you were doing. Maybe it was a time crunch issue or something like that. There were several students I noticed where, they did well for, call it 7 of 10 questions, and then clearly time was becoming an issue. Um, so, but yeah, so that's kind of where it sits on the exam. So actually, all in all, they were actually pretty good, but don't necessarily lose the faith if you did poorly in it. I would just try to ask yourself why you did poorly. Was it that you haven't been putting the time in? You didn't believe me when I said it's just going to take a lot of reps, a lot of hours. Programming is like a sport. You just have to do it. I didn't make the rules. If you want to get good at this, that's what it takes. Um, if it's just not your cup of tea, be honest with yourself. This isn't for everyone. And maybe, it's the type thing where you decide, well, I'm going to go maybe the direction. If I want to stay in computers, I'm going to go the direction of maybe something like a cybersecurity or something where I just need to get through the couple of coding classes and then somehow pass them and then get to the cybersecurity thing. Or maybe you just decide, hey, I like computers, but I didn't know computer science was this, something like that. So just try to be honest with yourself as to where, why you did poorly. I would say a very common situation for right now is that you're working hard, you're doing everything you think you need to do, and it just hasn't clicked yet. That's normal. It's very, very common that we'll have a student come in and get like a 15% on the midterm, and then sometime between the midterm and the final, things start clicking and it just starts making sense. And it almost happens overnight. You'll see all these things kind of line up. And then they'll come in and get a 97 on the final, which will then replace their midterm exam grade. And they end up with a A in the class. Everything's fine. So at this point, everybody can still get an A. Just try to be honest with yourself as to what the problem was. Um, Another thing I saw on the exams, this is just from a couple of people, and I made a note on your exam about this, but I mean, I tried to be reasonable because a lot of times it's just a suspicion. When I think I had mentioned in here before that when you've been programming for a long time, it's pretty clear when you look at code whether this person largely knows what they're doing or largely doesn't. My intention is always that when you solve problems, whether it's homework assignments or on exams, that I want you to only use the stuff we've introduced in class. I'm kind of almost putting boundaries in place that there are solutions to built into languages, but I want you to solve it using only the things you have available because that gets you down a lesson path. I didn't specifically say that on the exam, so I didn't take off points for it. But there were a couple of people who were using um, a lot of tools in the language that we have not introduced, and some of them are fairly advanced tools and advanced libraries. Now, does that mean the student cheated? Not necessarily. Maybe they've had a lot of this stuff before, and that's just the way they solve problems. Um, and they didn't, I guess, dumb it down to only using the tools from class. But I think just as likely, If you're really struggling with programming, you use tools like ChatGPT or something like that. It's probably going to use all the available libraries and stuff that might make the problem a little bit easier. So then you end up turning in something that you couldn't have done yourself. And it's pretty obvious to me that you're using all these extra tools, but it's not clear whether you just have some experience or whether you cheated. So at the end of the day, it doesn't mean I get paid either way. So you're only hurting yourself if you're taking those shortcuts. But at the very least, if you accidentally got a good grade on the exam, and, you know, at least in your internal dialogue, realize that okay, I didn't do this. Try to make some corrections before the final. I'll probably will put on the final note that you can only use things we've introduced in class. So that problem will probably backfire that time around. I'll just be able to take the points off. But at the same time, I don't want to discourage somebody who really is a strong programmer that just can't get out of their own way and do things the simpler way, or maybe not simpler way, but the less advanced way or something like that. So I guess consider that. Another thing that popped up in the exam, and it was relatively, I would say, unfortunate for it seemed like it was just one person that this really, I think, negatively impacted. They clearly know how to program because almost every one of their answers logically was mostly correct, but they didn't do anything inside of a function. They just wrote everything inside of main. And the thing is, they were putting little comments in there. They clearly knew what they were doing, right? They clearly know how to code. They were putting comments almost implying how easy the problem was, but I couldn't give them more than like half the points because they weren't answering the question from the exam. So really try to pay attention. I'm asking you to write a function. So I want to see, do you know how functions work, how the return types work? Do you know how to leverage the parameters? We've talked in class about, if you find yourself hard coding the values and the parameters or on the inside of your functions, you're asking the user for input, you're probably not doing what I'm expecting. I want you to write generic functions that take inputs in, then you operate your logic off of those inputs, whatever value they may hold. All right. All right. So any questions about the exam or anything like that before we move on? I've already emailed a couple of people. So if you don't get an email from me encouraging you to consider other options, I would encourage you to stick with this, but go through that process of asking yourself, why did I do poorly on this exam or something like that. Typically I'm not necessarily in the business of failing tons of people. I would say the only way you'd probably really fail the class is if you just didn't participate. I probably spread that C- range, D range out pretty far, where the chances of you sticking it with the class and not getting through it, as long as you're doing all the homework and stuff, is pretty low. You probably have to earn the A or B. But I wouldn't be too concerned if you're somebody who's working your butt off and like, okay, well, this is not my thing, but I need these classes. So you'll probably get through. Just keep up the hard work and maybe one day it will click. So hopefully that makes some of you feel a little bit better. Yeah. So let's pick up where we left off last time. We started talking about I've advertised it as kind of a new primitive type called pointers. It really isn't a new primitive type. That was another thing on the exam. Some of those people that used more advanced things used a lot of pointers in their answers, which doesn't mean that they didn't do their own work. It looks suspicious. So anyways, a pointer really isn't a primitive type so much as you don't create a variable of type generic pointer, although you can. Typically what you say is, oh, I want to hold a memory address and I'm going to hold a memory address for a reason. We'll talk about what some of those reasons might be. So you kind of modify existing pointers, existing primitive types. You might say, oh, instead of holding an integer, I want to hold the address to an integer. So your type would be an int pointer. We talked about last time that a memory address looks kind of like that. It's just a hexadecimal number, meaning something really big. And the reason for that is memory in our computers, all the memory is on one big long street. So we just number those buckets of memory, bucket 1, bucket 2, bucket 3, bucket F, bucket 1A, blah, blah, blah. All right. So let's go and look at some stuff in code. All right, so I'm going to say using namespace, standard. So for example, if I want to hold a variable a integer, we'll say int a equals 5. I can say int pointer b. So notice the variable type, instead of an int, it's an int pointer, int star. So we put an asterisk at the end of it. Now, you will see some people write it like that. Don't do that. It's technically correct because C++ doesn't really care. But typically when we talk about defining things, it is type followed by var name equals value, something like that. The type here is int pointer. The type here is int. All right. So we might say int pointer b is equal to the address of a. So we really have two special syntaxes for working with pointers. The asterisks and the ampersand. When defining a pointer using an asterisk indicates we are holding the address of something. When using a variable of type pointer using an asterisk indicates that we want the value that lives at that address. All right, so we got to look at it from the perspective of, are we creating a brand new variable? If so, like we did here, when I use the asterisk right here, I'm saying I want to create a variable capable of holding an integer address, int pointer. As opposed to, if I were to do a cout on B, so I didn't use any special syntax there, but notice that B is of type pointer. So if I were to cout on B, B is a variable capable of holding a memory address. We expect this to output a memory address. That's what B holds. It holds integer pointers, addresses to integers. What would be the difference between an address to an integer and an address to a char? Aren't addresses addresses? How big is a integer? 32 bits, 4 bytes. How big is a char? Depends on your language, either 8 or 16 bits. C++, it's 8 bits because it operates off of ASCII, the ASCII character table. Most modern languages operate off Unicode, which is 16 bits. So anyway, you cut it, an int is larger than a char in any language. So the difference between an integer pointer and a char pointer would be not the difference in the number. They're both going to just have a hexadecimal number telling you where this is found. The thing is when it goes to that address and it says, give me the char that lives at that address, because it's a char pointer, it's only going to look at the first 16 bits or the first 8 bits at that address. Because that memory address, however big the bucket is, depending on the operating system, maybe it's a 64-bit bucket, 8 bytes, something like that. If you have this bucket here, but you've dedicated it, you said this bucket holds a char. We're only actually going to use a portion of that bucket for holding a value. So yeah, we're wasting some space because you can't hold two different things at the same memory address. So you might say if you're using an operating system that uses a 64-bit uh, memory size, so if you think of the memory as like a big long street with a bunch of houses on it, you're saying, okay, the maximum size house is 64 bits. So all the lots on that street, maybe we translate it into real life, maybe they're all the acre lot. Okay, not all houses fill that entire lot, right? So if you store a char there, you're only going to be using a quarter of the space that's available, which means then you've wasted some other space in there. Not a problem. We have a lot of memory, right? But when you take the operating systems class, that's something called internal fragmentation. It's memory you have, but you chose not to use it, and you can't use it for anything else. It's wasted memory, but just get more memory. It's not a big deal. Whereas an int, that's going to be a little bit bigger house, right? So an int pointer and a char pointer, both are just hexadecimal values. They point to a location in memory, but the type of pointer you're dealing with implies how many bits at that location I should look at to get the value. Make sense? An int uses more bits to represent. It uses 32 bits than a char, which uses in C++ uses 8 bits. So if I go and I say, give me the value at this char pointer, I'm saying only go there and tell me what value lived at the first 8 bits. Don't read the whole thing. All right. That's important because the whole thing, let's assume that all this wasted space was a bunch of zeros. So you initialize this memory location to 0. All right. Then you put a char there. So now you had let's say it was 64 zeros at this memory location. So now the first 8 bits of that are now going to be zeros and ones, some mixture that gives you the value of the ASCII value for that char, right? But if you read that number as the entire 64 bits, you'd end up with some giant number, right? Because the first 56 bits are zeros. The far right bit is the ones place, the twos place, the fours, the eights, the 16s. By the time you get to the 8 bits representing your number, you're already at 2 to the 58th power, to the 56th power. Big number. Big number. Not the correct number. ASCII only goes up to 255. All right, so the type of pointer is important to tell the computer when you say, give me the value that lives there, to say, how many bits should I take into consideration when reading that value? Make some sense? You don't really need to worry about the memory stuff happening under the scene in this class, but we want to appreciate that that's there because next semester, when you take computer organization and architecture, you're going to be specifically talking about those bits that are under the hood. And the semester after that, when you take operating systems, you'll be talking about that stuff like the internal fragmentation and things like that. All these things are interconnected. All right, so back to my example here. I've created a normal plain Jane variable a, int a equals 5. If I print out a, it's going to print out a 5. We've seen that plenty of times, right? We don't need to be convinced of that. Then I've created another variable named b, and it's built to hold this kind of value, this type of value, an int pointer. That is the address of an integer. And what did I put in there? I put in the address of a. Not the value of a, but where in memory a lives. So if I go to print out the value of b, it's going to show me the memory address. You got this. So there's my memory address. On the very next line, if I instead say, give me star b, I'm saying, give me the value that lives at that memory address. And what value lives there? My 5, right? So there's my 5. And I'll just put one more thing here so we can. So we actually have synonyms for getting to that 5. We know we can directly access the 5 through my variable A. We've done that a bunch of times. We could put the address of A inside of a variable. And if we print out that variable, we get the address printed out. We could also print out, instead of putting it in a variable, we could just say, give me the address of A. Address of A is what we used right here. It's the value we put into my variable B. So saying B and saying ampersand A, same thing. They're the same value. So we're going to get the value of A holds a number 5. The value of B holds a memory address because it's an int pointer. The value of the address of A, ampersand A, holds the memory address that the operating system gave us to hold that 5. And star B says, go to the memory address that's stored in B and tell me what value did you find there. That's what star B says. This should be 5, same address, 5. Okay. Now, before I go any farther, questions on this? It's not difficult, but I've already told you that pointers is where a lot of people start freaking out. There's enough things going on here. When you start seeing scary memory addresses here, your brain goes to mush. And you start getting scared or intimidated or whatever it is, and these things don't stick. So before we go any further, we have, let's call it as simple of an example around pointers as we can create. Let's make sure we okay. So let me start recording again. And just as a so is the internet was doing something funky? So pointers, even the Zoom got intimidated? That makes sense. That checks out. All right, so let me pause. I'll resume the recording, so hopefully it records correctly. All right, so for the sake of this, let me just go and explain this example again one more time for everybody to make sure it's getting recorded correctly. All right, so we're introducing pointers here. Remember, a pointer, any kind of pointer, holds a memory address. So it'll hold something that looks like that. Scary hex number. So I'm going to create a couple of variables here. The first variable is a normal integer. Variable name A, capable of holding a whole 32-bit signed integer. I'm going to go ahead and throw a 5 in there. If I were to print out A, it's going to print out the 5. Right there. No surprises there. I'm then going to create another variable named B. But the type of value B is built to hold is an int pointer. That is the address of an integer. So this is a new variable type for us. So all our new variable types are basically all our primitive types with stars after them. So we have short pointer, int pointer, long pointer, char pointer, bool pointer, float pointer, double pointer. And technically byte pointer, but I think we saw C++. It's probably byte's probably living in one of the other libraries. But it's there in C# and Java. All right, so we now have pointer versions of all our primitive types. And they're capable of holding the address of that kind of value. Where all addresses look the same, but having a type associated with the address lets the computer know that when you go to that address and go to read the value, how many bits it should look at for getting you the value. Make sense? All right. So go ahead.
So ampersand A, the ampersand means
The address.
If you were just type int b is equal to ampersand a, what would it?
Oh, so if I said this, oh, it should scream at us. Can't convert between a int pointer, a memory address, and an int. That is, don't try to shove a memory address into something built for holding a number, a 32-bit signed number. So, and that's really not a new error either. We would get the exact same thing if we tried to put a float into actually, would we? Would we get the same thing if we tried to put a float into a int? It would probably just truncate. We might get a warning. Usually it's like a loss of precision warning, I think, is kind of what you would usually see. But generally speaking, we want to deal with compatible types. So if you're going to create a memory location to hold something, the thing you put in there should be that kind of something. Where in this case, I'm saying I want to store an address. Specifically as an address of an integer, because that's what A is. A is an integer. I'm saying, tell me where that integer is in memory. I can only hold that value inside of a variable that knows how to hold addresses, specifically integer addresses. But in this case, by your example, you were saying, hey, let's try to throw that in an int and see what happens. Wasn't happy. All right, so let me put the int star back in here. All right, so I've created two different variables here. Nothing new from a create variables perspective. I've just added a new type of value we can store. Go ahead.
Just to make sure I'm getting this correctly. So the first print of A is just a normal integer. It's 32-bit.
This line right here? Yep, that's just printing out an int. Nothing new. B is a variable. B is a variable of type int pointer. So that means it's built to hold memory addresses specifically that point to integers. And we call them pointers because we imagine that we have this, I keep using the center of the room here for some reason where our big long street is, where our memory is. We call a pointer something because it points. It's that house down there. We're pointing to a memory location. Okay. We have the same thing in real life, right? If you're having a party at your house tonight, do you hand me the house and tell me to open the door at 8? Or do you give me the address of where I can go and locate your house and find it? You point to, oh yeah, I live down there. I have the address. I plug it into my GPS and then follow the blue line, right? Go ahead. So I'm going to confuse 90% of the class if I answer that right now. His question was, what's the point of using a pointer effectively, right? We're going to be seeing that during this class. As soon as I get past this little hurdle, we're going to get the why we might want to use pointers as opposed to, hey, this is computer science trivia and just use pointers because it makes you look cool. Which is, by the way, what it looked like on some of the exams where people use pointers. They were just randomly using pointers just because, I guess they thought it looked cool. Because sometimes they weren't calling their functions right. They would have the whole thing where it was using their function. They were expecting an address, yet they were passing in a value. So they were going to get the error that you just created for us. But, yeah, whatever. All right. So we will be answering the question of why we might want to pointer shortly. All right. So creating two variables. One holds an int. One holds the address of an int. That's all we've created there. Then we're going to try to understand the different values. So we'll go ahead. Our very first one's just a repeat. Print out the value of A. A is an int, so it's going to give us its value, which is a 5. The next line says, print out the value of B. B is an int pointer, which means its value will be the memory address of an int. And we happened to build it that way. We said, hey, B, we want you to hold the address of A. This is that other side of the pointer syntax. The special syntax we have for pointers, we have asterisks and we have ampersands. Ampersands allow us to take a non-pointer value and get the memory address aspect of it. That's what that ampersand does. So I'm putting in the address of A here, which is going to be some memory address where this 5 lives. And I'm going to store that inside this variable B, which was specifically created to hold memory addresses. So far, so good. So when I go to print out B here, it's going to print out the value stored in my variable B, which I've advertised as an int pointer, which I've also put the address of an int into. So this is going to give us, let me run this again without my error. That's going to give us the memory address. What I have highlighted right there, that is the place in memory, the house on this street where I can find that 5. Next line here, I'm operating off the variable A, which we see is just an int, but I want to give you the address of A, where that int can be found. So I can do that without using a variable to hold the address. I can just say, hey, just give me the address of A, ampersand A. And we see it's the exact same value because the address of A is the value that we put into B. They're the same value. It's 2 different ways of getting at them. So we're going to get that same memory address again. And then lastly, I want to output something related to my variable B. Now we saw that when we just outputted B right here, we got a memory address. But if I want the value that lives at that memory address, I have to use star B. Star B says, give me the value that lives in that location, the memory address stored in B. What would happen if I said star A here? Go ahead. Well, we defined A. We defined A right here. Here's A. And if I say star A, what is, when I'm using a variable, not defining it, when I'm using a variable, let's go back here. When you're using a variable of type pointer, using an asterisk indicates that we want the value that lives at that address. So what is it going to try to do right there? Go ahead. Say it one more time. Okay, well, it's not going to find the 5. It's going to, if I'm saying, give me the value that lives at an address, it's going to view that 5 as an address. It's going to get short-circuited because A doesn't hold an address. But what I'm basically saying here is when I use the star here, I'm implying that the very next value here will be a memory address. So if we make the assumption that C++ doesn't yell at us for the type problem, it's going to treat the number 5, which is what A holds. It's going to treat that as a memory address. And it's going to say, give me the value that lives at memory address 5, which technically in most operating systems is actually super user space, so you wouldn't be able to access that. But it's no longer going to treat 5 as a numeric value 5. It's now going to treat 5 as a memory address. And it's going to go try to find the value you put there, and you had nothing to do with that. Whatever's living at memory address 5 or not living there, you weren't involved. Yet you're now trying to go and start messing with that, right? Because nothing keeps me from saying something like int star C is equal to 5. Saying that's a memory address. I just happen to know that's the memory address. Now, is 5 a legal 48-bit hexadecimal number? Sure. I just got to throw a bunch of zeros in front of it if I'm doing it in binary, but that's a legal number, right? First 9 or first 10 hex values are the same as the first 10 decimal values, 0 through 9. Then we start getting into the A's, the B's, the C's, so on and so forth. And then when you need to add another digit, hextet on. All right. So in this case, what we're implying here is when we say that star there, when we're using it, we're implying that we expect this value to be a memory address. Therefore, give me the value at that memory address. Invalid type argument of the asterisk, because you have an int after it, not an int pointer. So we would have had to say up here, it worked for the star B because we're using the star in the same way, but B did hold a memory address where A held an int. Right.
We were like 2 and B, would it make it an even bigger number, trying to make an address 100?
Yeah, so that's an interesting question. So what would happen if I said, give me the value of ampersand B? I get a memory address. Notice it's a little bit different memory address. That's the memory address where the variable B lives. Anytime that I create a variable of any kind, doesn't matter what type, I have to find a place in memory to store it. A variable is a name value pair. If I'm going to name something, I need to find a place in memory to put it, which means that my variable B, it lives somewhere. And what it holds is the location where something else lives. So as he pointed out, this is just going one extra level, right? So when I say, give me the value of B, it's printing on a memory address. This guy. When I say, give me the value of ampersand B, it's not giving me the memory address stored in B. It's giving me the memory address where B lives in memory. I have a variable somewhere named B, and I've put that somewhere up in memory, and the value I've put in there is the memory address of A, by our example here. But if I say, give me the address of B, I'm not asking for the value stored in B or the resolved value, because this is the value stored in B, which is this memory location. This says follow that memory address that's stored in B to its location and give me the value you found there. That's the 5, right? That's my 5. This guy says, don't follow that memory address. Instead, I don't want you to tell me what value is stored in B. I want you to tell me where in memory B is. Where am I storing a value? Where does B hold its value? It holds it in another location in memory because B has to live somewhere. So when we create variables, we're creating memory locations that we can refer back to later on, which means we need to put them somewhere in memory so that later on, when we reference that variable B, our computer knows how to look it up and where to get it. Go ahead.
So it's like finding that clue that's somewhere else, find the treasure.
Sure. Yeah, I mean, if you create a little scavenger hunt, right? You would have, you might hide one thing which gives you a clue to where the next thing is. In this case, it's not a clue, it's specifically a memory address, right? So you follow it, but at some point, all of your variables have to live somewhere. That's completely disconnected from the values they may hold. All right. So, any questions about that? I know it can feel confusing, but hopefully you're seeing it's not an overly complicated thing. You just have to slow yourself down and really walk through what's happening here. When you read this line, you want to resolve these variables. Often it's called, let me finish filling this out here real quick. Let's see, when defining a pointer using when using a variable, this is often called dereferencing a variable. Says to get the value that lives at a memory location. This is often called resolve. Get the value is resolve the value. Okay. Then this ampersand thing here says give me the memory address where the following variable lives in memory. Not the value stored in that variable, but the variable itself. And this is only when using a variable. It's going to probably add confusion to it. I guess what I mean by that is you would not do this. You can't, we don't have another collection of primitive variable types that can hold, that are called int ampersands. It's not a type. Types are either pointers or values. All right, we got those two options. So really, this ampersand thing is something we would only see when we're using it. Which would include if you write a function that's expecting to take a memory address, you could say, give me the memory address of something. So ampersands could be involved there. And we'll see that through examples. All right. So any other questions on this, at least as a baseline, and then you can go rewatch the videos and mess with this yourself a zillion times. You'll want to put the reps in here to make sure this, you can wrap your mind around this. But the important thing here is, and where it's connected to what we've been talking about up to this point, is slow yourself down and take the baby steps. This line right here, don't immediately see the A and ignore everything else. Ask yourself, what is really going on here? What is A? A is an int. What does ampersand mean? It means give me the address of something. So this is saying, give me the address of this integer, which is wherever that 5 is actually stored. Make sense? When I run into something like this, we glance, we see, oh, B. What kind of value is B? B is an integer pointer. So that means B holds a memory address. What does star mean when we're using the value? Star means give me the value that lives at a memory address, which says, go to this memory address and tell me the value you found there, which will be a 5. Because B holds the memory address, which is the address of A. And the value, star B, the value at that memory address is a 5. Okay. So now let's try to understand why we might want to use pointers. So I'm going to create a function here. We're going to say int, actually, we're going to say void change value. This will take in an int A. I'll go ahead and write this guy. And so what we'll do is we'll go ahead and we'll say A is equal to, I don't know, we're just going to say 13. And then I'm going to do C out A and L here. And I'll even do that beforehand. I'll throw all this inside of a comment for now, just so that code is still there. All right. So what I'm going to do is I'm going to say int A equals 5. Then I'll say C out A. Then I'll call change value, passing it A. Now keep in mind that this variable A and this variable A are different A's. They're in different scopes. This A is the number 5. This A is the number 5. This A here is whatever was passed into this function. So this A right here lives and dies with this function. Now you might say, well, why didn't you just name this variable something different? And you could, and you look at that now and you say, okay, well, now it's clear that they're different things. Okay. Neither of these are meaningful variable names. So this would be something that a bad programmer might do to avoid the error that they don't understand. You want to understand how scope works. You want to understand that this A and this A are different A's. And you want to remember, I think we have this on another slide too. I'll just say, remember, all variables resolve to their most local definition. Which means if I am inside this change value function and I say A will resolve to its most local definition, which is this guy right here. So when I'm talking about A in here, I'm talking about his most local definition, which is right there. From here, we actually don't have access to the definition in here. This variable lives and dies with main, just as this variable lives and dies with change value. So there, in both of these cases, there actually is only one local definition of those guys. It's just two different local definitions that just happen to have variables with the same name. All right, so change value is going to take some integer in as a parameter. We don't know what integer. It's just going to be something that is an integer. That means something that is negative 2.1 billion to positive 2.1 billion. Some number in that range is what this guy's going to take in. What am I going to do? I'm going to go ahead and print it out. Whatever it was, I'm just going to spit it out to the screen. Then I'm going to modify it. It's going to hard code it to 13. Then I'm going to print it out again. What's it going to print out on this line? Regardless of what value is passed in, what's it going to print out on line 40? Good. 13. Why? Changed it to 13. Changed it right there. Said print it out. It's changed. All right. So now back up here. We're going to output A. We start A off at 5. I'm going to output it. So we should see a 5 here, right? Then we're going to call this function. It's going to come in here. It's going to print out whatever A is here, which is also going to be a 5. Then we're going to change A to a 13, print it out again. Now it's going to print out a 13. What if I output A again after we've returned control back to main after that function? What will it print out right here? Back to 5, right? So this should be 5, 5, 13, 5. That's the order of operation, right? All programs begin and end with main. Main says define a variable A, print that A to the screen, call this function. This function takes in a variable, print that variable, change that variable, print that variable. This function ends. We're back to main, print out the value of A. So we see 5, 5, 13, 5. Go ahead.
In the change value, if we were to return, would it then be 5, 5, 13, 13?
You want to do that? Return A, like I have it written there? Yeah. So, okay, so he wants to return it, so we can say it's going to return an int. Now you're wondering, is it going to print out the 5? No. Why not? There's a rationale for that that's unrelated to what we talked about today. When I call change value here, what am I doing? What am I doing with the value that's returned from change value? Line 30 there is what I'm asking. What does that line do? That line calls a function. It happens to be, as we have it written right now, a function that returns a value, but we're not doing anything with that value. Now, what you are implying is, what if we overrode A with that changed value? A equals whatever change value returns. Now A will be that 13. But we did that indirectly by just saying, hey, I'm going to change it in here, and then I'm going to let you know about my change. All right, so that's not really the example we want to get across here, but you could do it that way. So let me get these back to void. All right, so at this point, we all see that this change we made to the variable here does not have side effect. It does not persist after this function ends. Because when we come back to main here on line 31, it's printing out the old value of A, which is 5. All right. So what if we wanted this function to modify that value permanently? Well, now we have the opportunity to say, rather than you creating a brand new variable here, why don't you give me the memory address of the variable you want me to change? I will then go to that location in memory and make my changes. All right. So we can say this guy takes in an int pointer A. Now, when I call it, I can no longer pass it an int. Why? Because it expects an int pointer. Let me fix it up in the prototype too. So now the parameter for this guy is expecting me to give it an integer pointer, which is the memory address to an int. So down here, he's taking in the memory address to an int. What's going to print out right here as I have it written? Some memory address, right? The address that I passed in, which I'm not doing a very good job of yet because I haven't called this guy correctly yet, right? Right now, I've passed it an int. It wants an int pointer. So if I have a function here, change value, that expects an int pointer, and I want to pass my variable A to it, how do I need to pass A to this thing? When I do my input, what do I send? Go ahead. Ampersand A. Change value expects the address of an integer, so I'm going to give it the address of an integer. So again, now we're in here. If I say C out A, I'm going to print out a memory address. What if I wanted to print out, in this case, the 5? What change can I make here for the 5? I know he knows. Asterisk. So we're going to say print out star A, the value that lives at that memory address. Then I'm going to say change A to 13. What's that going to try to do? What is A? On line 39 right there, what is A? What kind of animal is A? Go ahead. Int pointer. So A is a variable that knows how to hold a memory address for an integer. So if I'm changing the value of A to 13, what am I trying to do there? Go ahead. I'm basically saying, A, you no longer hold whatever presumably important memory location you used to hold. Now you just get this memory location 13 that I just made up, that I never checked with the operating system to see if it was available. I'm stealing land. What we're actually seeing right here is something that a lot of hacks take advantage of. If you're somebody who has written viruses or hacking computers or whatever, all this stuff you see on the news and stuff like that, you'll notice that a lot of them use older programming languages like C that have less protections, because those languages allow you to walk around memory that you don't own with little oversight, where newer languages take extensive precautions to protect your operating system from you going on to property that you don't own. All right. So what we're trying to do right here, it's going to yell at us because 13 is an integer and not a memory address. We would have to flag it as a hexadecimal value. We're not going to go down that path necessarily, but what I'm attempting to do here is I'm saying, look, A, whatever you used to hold, and A is an int pointer, so he used to hold some memory address. I don't care what that is. I want you to overwrite it with 13. And even if we assume 13 is a memory address, I've presented it to it as a memory address. There was never a situation here where I asked the operating system for memory address 13. I picked it out of the sky. So this is equivalent to in real life. You just driving down the street, you see a plot of land that either has a house on it or doesn't. Doesn't really matter. You pull in, you say, this is mine. You just zip into the driveway. You're going old school. The boat comes up on the shores. You claim this land is yours. You have to carry around a flag, right? You got to have your own flag. All right. So we're stealing land, presumably, from the operating system here because we never asked for permission. We never bought it from somebody. We didn't have the title switched over to our name. We're stealing land. We're trying to steal land. All right. So this isn't going to fly anyways. Go ahead. Yep. So if my intention here actually is to change the value that lives at A to a 13, we would say star A gets the value 13. I'll often read this single equal sign, the assignment operator. You'll hear me often refer to it as gets the value. Really trying to force that difference between the double equal sign, which is the equivalence Boolean operator, and the single equal sign, which is the assignment operator. I'll usually read that as gets the value. So now I'm saying replace the value that lives at memory address stored in A with this 13. What's going to print out right here? Me changing the value that lives at that memory address, does that change the value of A? A is a variable capable of holding a memory address. Star A is the value that lives at that memory address over there. So if I change star A, I'm changing this variable over here. I'm changing the 5 to a 13. If I were then to print out the value of A, not star A, has this memory address where A lives, is that any different? Or the memory address that A holds? I haven't changed its memory address at all. It's still pointing to this place over here. I've just changed the value that lives over here. I'll draw a picture here in a second, but let's just see this go through. So I start my integer off at A. I output A, which is going to be a 5. A started off as 5. I'll call change value, passing it the address of A. Why? Because it expected me to give it an address. Then I outputted the value found at that address, which again is going to be a 5. Then I'm changing the value that lives at that address to a 13. Then I'm going to print out the value at that address again, which is now going to be a 13. Then this function ends. So we just finished this line right here. So now 31 says output the current value of A. Now, remember, variables resolve to their most local scope. A's most local scope is this guy right here. He used to hold a 5. But when I pass in that memory address here, and I change the value at that actual location, that value will now be changed here. So we have our 13. It was able to escape the function because I didn't work with a local variable inside the function. I worked with that variable that's up in the sky, and I passed to this function that place. If I give you my address and you run to my house and spray paint my garage, when I get home, I'm going to have a spray painted garage, right? You weren't working with a copy of my house. It's the real deal. Go ahead.
The 5, like, you set the variable 5 and see out,
Mm.
okay.
That's thanks to him. He taught me that I have to scroll up 7 classes ago or something. I pay very little attention with what's in front of me because my eyes actually don't work out very well. I have pretty bad eyesight. I'm supposed to wear trifocals because I can't see up close, but I do so much VR stuff that I wear contacts. So I can barely see what's in front of me here. But I can see in VR really well. Go ahead.
Is this equivalent to more or less defining A and then saying that A is equal to the function?
No, because we're not change value is not spitting a value back out. So let me draw a picture. Because right now I'm doing a lot of hand pointing things, right? Which probably is not helping the Zoom people very much at all. But trust me, I look great while I'm doing it. All right, so I agree with that, right? Remember, I'm curving your exams potentially. All right. So let's draw a picture of what's actually going on with this code here. All right, so pointer example. And what I'm going to do for this guy, yeah, we'll refer back to the code. We'll see if there's a way for us to put that in later. All right, so we're going to do this pointer example here. Let me hide this. All right. So we have this variable int a is equal to 5. All right, we did that inside main. So here I'll actually label that. We'll say this is in main. Int a is equal to 5. Just let it be capitalized so I don't drive myself crazy. All right, so int a equals 5. So what that's going to do, this is inside main. That is going to create a place in memory. Let's just keep it simple. Let's say that's memory address 100. Let's go with red for addresses and green for value. All right. So this is the memory address. I'm going to label that guy here. And here, if you we'll say AB4 hex. Now it looks more like a short memory address. The little H at the end of it, that's how in a programming language you can specify you want this viewed as a hexadecimal value. It's not going to be a common thing you're going to do. Generally speaking, if you're working with memory addresses, you're working with stuff that was handed to you by the operating system. But if you're one of those folks who perhaps has tried to bypass the rules of video games or something like that with bots, and how many of you have ever run a bot for a video game? Academically, of course, right? If you were to look at the source code of those, a lot of times what they'll do is they'll hard code the memory addresses where stuff is loaded in the game, and they'll make changes directly to those memory addresses. And that's why you'll often see that your bot breaks when there's a software update to the game, and you have to wait a couple of days for them to update the bot with the new location of the memory addresses. So imagine this being like a competition between the game designers and the people trying to cheat at the game. The people cheating at the game see, well, how can I modify computer memory that this game is using to my advantage? The game designers are saying, we know this is going on, so we're going to try to make these memory locations change so that at the very least, the bot people have to make modifications. Now, why do you think the game people don't just use the operating system to hand them random memory addresses? Why do they hard code their memory addresses? Games need to be fast. So if you spend time asking the operating system to give you a plot of land, that's time. Might feel fast to us, but if you have a zillion people playing those games, good example is like World of Warcraft. World of Warcraft had zillions of people botting that game. But that's the kind of stuff that's happening. So realistically speaking, unless you are doing something probably nefarious, doesn't have to be, but it's likely you're in a gray area at best. That would be the only time when you would invent your own memory address because you know where you're trying to go. A majority of the time, your memory addresses will be handed to you by the operating system. Make some sense? All right. So we're going to say we have int a equal 5. This is a normal integer, plain Jane variable. There's its value. So here I'll value at that address. Memory address, here's the value at that memory address. All right, so now when I say cout a, and I'm not going to put the endels on here, it's going to say, give me the value that's there, 5. Now we have this other function, change value. I'll grab the header for it. So now we have another scope, right? Main is a scope, and here's a scope for this, this function. So if I then pass change value, the address of A, what I'll be passing in here is AB4H because this is expecting a pointer. So receives AB4H, not 5. So far, so good. Then we're going to say cout star A. Star A says, go to this memory address, give me the value that lives there, 5. Then we're going to say star A gets, what did I say, 13? Equals 13. When I say this, I'm saying A is a memory address, change the value at that memory address. So A says, go here. The value there is right there. And I'm saying change that to a 13. Now, if I cout star A again, I get my 13, right? And then when this function ends, if I cout A up here, A is an integer. A lives in memory right here. If you want to see what I mean by pointer, we have A here. A is a variable that lives in memory here. But since A is built for holding a value, it lives at this memory address. That's where A actually is. It's at that memory address. But its value is 13. So this is effectively A right here. The pointer to A, Actually, let's do it off of this guy. This guy right here. Ampersand A. That points there. We're talking about the same place, but the difference is, are we talking about its location or its value? So if we walk through this code here, int A equals 5. There's my 5. C out A, it's going to print out a 5. Now call change value, but pass it the address of A, this guy up here. Change value is going to take that value in, the address. First thing we're going to do is we're going to say, go ahead and display the value at that address. So we're going to go to the address. We're going to say the value there is a 5. It's going to print out the 5. Then we're going to say, change the value at that address to a 13. We're going to go to that address. Here's its value. We're going to modify it to 13. Then we're going to say, print out the value at this address. We're going to go to the address. We're going to go to its value. We're going to print out a 13. This function then ends. So we just finished this line right here. So we're going to go to this line, which says C out A. A lives right there. Current value is 13. So because we pass in an address, the changes we made, making sure we use the correct pointer syntax, were changes to the actual location in memory, rather than a copy of that value when we were just taking in int A as a parameter. So in a roundabout way, he asked the question a while ago, why would we use pointers? Yay. Why use pointers? Couple different reasons. One reason is it allows us to pass values to functions, allowing those functions to make permanent changes to those values in real memory rather than a copy of the value. That's one thing it lets us do. Sometimes we want that, sometimes we don't. Sometimes you want to send the current value of a variable into a function with the expectation that function is going to do something that potentially destroy that variable, make all sorts of changes to it. But when you come back to the program, you want to operate off the old value. You don't want the function to have side effect. Sometimes that's what your goal is. I want you to work with this value. But so for instance, if you want to borrow a quarter and I hand you a quarter, my expectation is that's not going to destroy the other quarter in my pocket. You're getting a copy of a quarter. This is for you. Whatever you do with this has no impact on me except I've lost a quarter, right? But sometimes you want to pass a value that you want to give them access to the real location. So in that case, I'm not giving you the quarter. I'm saying, here's a little piece of paper. You can find the quarter on the ground around the corner. Here's the address where you can find that quarter. Now you're working with the real place. The one other thing, and then I know we're out of time, is pointers are often smaller in size than a value. So for instance, an int is 32 bits. A long is 64 bits. A pointer in modern operating systems is typically 48 bits. So that's 64 bits, 16 for root user, 48 for user. They just split up the memory space a little bit. So at the very least, we can see that between these, a pointer is a smaller value than a long, but only a little bit bigger than an int. But if we imagine in real life, if I give you the address of my house on a Post-it note, that's tiny, right? But if I hand you the house, not so tiny, houses are heavy. A lot cheaper to hand an address than the house. All right, so we'll stop there. Didn't quite get to where I need for homework, so I'll make sure the assignment over the weekend's extra hard. For next class, really try to go through what we looked at today. It was only like 7 or 8 lines of code, but that's a really important code that you understand that and really train yourself to slow down each line and say what is really going on here. Don't just let your eyes glance at a variable name and immediately draw conclusions. All right. I'll see everybody on Thursday.